Swayam Prabha. Digital India. Educated India.
So there is something called KKT conditions, and which will have. Have you heard about it? This KKT conditions, I don't know. So this one thing is. So when we have, so this is Lagrangian functions with our primal set of variable and with our dual set of variable, and we are deriving it with the primal set, and then this is equal to 0. This is called the stationary condition. Of on primal variable. And also we want primal feasibility. So we want all the constraints on W satisfy. So that is called the primal feasibility. So here we want W transpose Xi plus B greater than equal to 1 minus xi I for all I. And also we want xi I greater than equal to 0. These two constraints were there in our primal problem. And we have something called dual feasibility. Okay. So now maybe I should write it here. So we are doing this optimization problem. So this is our primal optimization problem. Maybe I should write W everywhere here. How we'll define that Lagrangian function for this optimization problem? So Lagrangian function will be defined as so we'll take everything into the function, all this left hand side, this gi's and hi's, and we'll have some multiplier with it, and we'll take the sum over all the constraint, and how this multiplier should be. So this is greater than equal to 0, but bi can be anything, unrestricted. Okay. So this is how we get this Lagrangian function. So this will then have all the parameters, primal parameters and dual parameters. For us, we do not have any beta because we do not have any equality problem in equality constraint in SVM. We have all the non-inequality constraints, so we have used the alpha and the gamma. And we also have this alpha I greater than equal to 0 and the gamma I greater than equal to 0. So maybe I'll go to the another page and we'll see what is our minimization problem here. It was this by 2, and then we have this yi W transpose Xi plus B is greater than equal to 1 minus xi I, which we can write if we want to write in this form. So less than equal to 0 form, we'll be writing it. Yes, okay. So then it will be what? 1 minus Ii minus minus Yi W transpose Xi plus B less than equal to 0, right? And we have this Xi greater than equal to 0, so we will be again writing it as a gamma I, we will be writing it as a minus of Xi is less than equal to 0, and therefore our Lagrangian function will be this W, and then we will be having a sum over gamma this I 1 minus Xi Yi W transpose Xi plus B, and then we will be having again this is like minus sum of gamma I Xi, okay, and we will be having this dual feasibility, that's all this are 0 and this are also 0. This is the dual feasibility. This is the thing only I have, so you have here. So I have taken the other sign, so that's minus sign was not there for me, but it is the same thing, same dual functions. And then we have this primal feasibility stationary condition, and along with that we have this other primal feasibility condition and dual feasibility conditions, and along with that we have something else. So it is a primal feasibility, it is stationary, and the dual feasibility, and something else is called the complementary slackness. Which will say that dual variable and multiply by the primal constraint. So it's a dual variable and the primal, all the primal constraints, these are 0 for all the constraint. So if you use this set of conditions and if you replace your W, all the primal variables from your Lagrangian function, then you will get. So I think it is better to try it yourself, how you will get it. So you have this Lagrangian function, and you have this set of conditions, and the task is to remove primal variable from the Lagrangian function using these conditions, and then you will get this optimization problem defined on only on dual variables alpha, and even this does not have gamma. You can see that we can remove gamma. I am not going in the detailed derivation. And then we want to do a maximizations of this, and we maximize this. That I am the truthful to you, and this will be your dual SVM function, and you will be able to maximize it with respect to alpha. But how to get your hyperplane? How to classify your test data? You have, for classifying your test data, you need to find out W transpose X plus B, whether this is greater than 0 or not. So from again this alpha, you can find out what is the W. This is the W with your optimal alpha, okay, and you can calculate the B even with help of these data points. And now for a test data xt, you will be calculating these terms to classifying it. So B will be a constant along with this, right? Okay. Now one thing here, who is helping you to define your hyperplane? Which alphas? Those alphas which has some non-zero numbers, right? If the alpha is equal to 0, then it is not helping you to define your classifier. Do you remember? We were defining our supporting hyperplanes with the help of the support points. So it turns out that this alpha I will be greater than 0, a non-zero number, when they are that supportive points. So that's why when alpha I greater than 0 in the dual optimization problem, we call these points are support vectors. So this classifier is defined only on the support vectors. When the alphas are 0, then when they are not in the supporting, they are not on the they are not supporting point. That means they are correctly classified. Supporting points are not only those points who are on the supporting hyperplanes, but also there are these alphas are non-zero for other misclassified points. Okay, but alphas are 0 for the samples which has correctly classified. Good. Now here I am one thing. Now check in the dual formulations. Are we using, when we are optimizing our dual formulations, we are not directly using our features vectors. Why? In our optimization problem, we have only an inner product between two feature vector. And when we are defining the hyperplanes also, we have this inner product, right? Sorry, when we are defining the class label of a test data point, that is also has an inner product between the two feature. Then if we are dealing with the dual optimization problem of support vector, you need to input your model the feature vectors, but you can input the all possible this inner product between your sample points. So what will be the size of that matrix? N cross n, where each element, ij element, will be having the inner product between the xi and xj. This matrix we called kernel matrix, kernel gram matrix. So now we are slowly getting into the kernel methods. So kernel methods is like we want a function that will somehow give an inner product between the two samples, maybe in the original space or in some higher dimensional space. On the other hand, you can think about, you are trying to define some similarity measure between the two feature vector. It can be a linear similarity like an inner product. It can be a non-linear similarity like a Gaussian or Euclidean distance between the two points. So each Kij is giving a similarity measure of between two samples. And then when you are finding a gram matrix of this kernel on this your sample, this gram matrix should be positive semi-definite. Your similarity measure should be like that. When a matrix is called a positive semi-definite, so here we want a kernel function, so that kernel ij is going to somehow give you the similarity between two points xi and xj, such that when you have a kernel matrix, this is a kernel matrix where each point this is a kij, such that this is going to be positive semi-definite. And what does it mean by positive semi-definite? If you have all the point x which is in the same samples, and then x transpose kx which has in the same space, then this is going to be 0. If your matrix satisfy this K matrix satisfy these conditions, then we will call it as a positive semi-definite. So there are some theorem also, this is called Mercer theorem, which has some other interpretation, maybe we are not going through that details. But you have, somebody has some questions like how to define a kernel functions. So yeah, so it should be in some reproducing kernel Hilbert space, but in a vague way you can see that if you can define a similarity measure which will result into a positive semi-definite gram matrix for all possible samples, then you are done. Otherwise, yes.
I read it somewhere that to define some new kernel, we have to do two things. One is that they must satisfy the KKT conditions, and another is they must satisfy Mercer's condition.
Okay, no, it is not the KKT conditions. Marx's theorem is correct. KKT condition is not related to the kernel definition of the kernel. KKT conditions is related to the how to find out the primal, how to get the dual optimization problem. It's not.
And what Mercer's condition are helping us in kernel?
Okay, so Marx's conditions is these things. So you can define your kernel in this way, like you have 2 points and you just put these 2 points in some other space using the feature vector, and then you have some positive non-negative numbers you can add also, and then this is your the similarity matrix. This can be the infinite number of features. If this is your similarity matrix you are calling, and then if you are defining the kernel in this way, so this is called the Mercer theorem. So if your kernel is satisfying this condition, like you have transfer your data, so from x to you have transfer phi 1x, this is your basis function, phi 2x, and this can go up to phi infinite of x, and you are defining the kernel between ij, the similarity between the xi and the xj is sum of theta j, maybe I can theta d is the number of the dimensions you have in this transform space, and then this will be the phi d of xi and the phi d of xj. And if you define your kernel like this is called the Mercer kernel, and this will be the valid kernel. This is the Mercer theorem. So one way that you have to find space, you take it to the phi x and then take a linear like inner product in that space. This will give you a kernel. Or you can find a similarity measure in your this original space, which will give a positive semi-definite matrix, then it will be also your kernel. So in the kernel support vector machine, we just replace these things, this inner product, as kij, the kernel value between I and j. And when we will be predict the class also for unknown data set t, sample xt, then also will require that kit. So if we replace this thing, then we will be having a kernelized SVM. So here is two example of the kernel we generally use for SVM is hugely used. One is the polynomial kernel, that is defined like this. This is take the polynomial of degree d, and this is the kernel, it's called Gaussian kernel or radius basis kernel. Here also this lambda is a hyperparameter which you can decide with the cross validation. D is also a hyperparameter which you can decide with the cross validation. Okay. So the same way, once we get this thing using these kernels, we will be having the value what is W transpose phi x plus b, and that to find that we can use this equation, and then again the final classification will be depending on the sign of that functional value. So when in the same data set we run some kernel with RBF and this Gaussian radial basis function, and the left hand side shows the radius basis function and the right hand side shows the degree of the polynomial of degree 3, and then we are for the training data we are getting both the same accuracy. But when we do the test on the test data, we can see that maybe this has the more complex structure, this radial basis kernel, but still the test error is less than the polynomial kernel. But if you take here we have also did the optimize the lambda value, the kernel width of the radial basis function, that is this one, this lambda. But if we take very very high lambda, maybe in that case we will get more complex decision boundary. That could not be the better, the good thing to do. I think I did not cover this multiple kernel learning because it will be little different things. So, but those who have questions over SVM and the kernelized SVM, did you get something, or I think you have questions, so you can ask.
There are other methods as well in the market, like neural networks, which are better than SVM. But where to use SVM and where to use other things?
Okay. So, in general, this decision tree and the SVM are hugely used for the cases where you have lots of dimensions, a huge dimensional data set, but you have less number of samples. So, SVM and DT are used in biological data a lot, because in most of the cases biological data has like 10,000 genes, but you have the samples only 5 or 10 samples. So, in that case, these are the useful, because the neural network needs a large number of data sample to learn it properly. So, that is why this is the era of big data, large data. So, that is why in this time we are mainly focusing on the deep learning neural network, because this has the capacity of handling large number of data very efficiently. But surprisingly, the people has used this CNN for CV, like computer vision. But for the text data also, people are now struggling to use neural network. But for biological data, it's still very hard, difficult to learn a neural network for biological data.
Can we say that if the data set is small enough, finite enough for SVM, of course NN can be used there, SVM give a good quality in comparison to NN?
So theoretically, you cannot say, because theoretically the number of the if your deep network have exactly accurate number of nodes in per layer, exactly the correct number of layers, then the kernel you are using for the SVM, it will be producing the similar effect, exactly the same effect. Then that will be performing, both will be same. But interpretation wise, the SVM or the kernel, they are better, because you know you are using polynomial kernel. So your classifier will be exactly a polynomial classifier, a quadratic kernel, a quadratic classifier. But for neural network, it's hard to interpret in this way. What is happening inside, you don't know much. So even for the lesser number of samples, you can learn both the things. But in the neural network, how we learn, we actually give the more samples, and we learn it at sample wise, like in the iterative learning, and that's why it do not mean solve much optimization problem. What I know means how it is now working. It's that it generally takes lots of data to fix your parameter, because when it is SVM, your parameter will depend on the number of samples. So it is if you have 10 samples, you have 10 parameters, 10 alpha. So you are learning only 10 parameters. But when you have the number of samples 10, but you have like thousands dimensions, then for neural network, you will have thousands multiplied by number of nodes you have. So that much huge parameter. So learning n number of parameters, have you learned these BC dimensions? No. Yes or no? Yes. So learning some like n numbers of parameter, you need at least some n plus 1 data samples, which are linearly independent. So when you have 10,000 parameter, but you have 10 data points, then you cannot learn it. where SVM will have lesser number of parameter. Then you can learn it. Any other? Okay. So we are done. So thank you very much. I found this SVN session was more interactive. And this is my email ID, and feel free to ask any questions you have, and I'll try to reply. I'll reply you. Maybe I'll be not able to reply in the same day, but keep patience, I'll reply you. Okay.